You know, when you look up at the sun, it seems like this steady, giant ball of light, right? But what if I told you it has weather? And I'm not talking about clouds or rain. I'm talking about massive, churning storms of plasma, continent-sized currents, and gigantic flows that dictate everything from sunspots to solar flares. Today, we're going to go inside our star and actually map its incredible internal weather system. Okay, but that begs a pretty huge question, doesn't it? The sun's core is millions of degrees. Its surface is a boiling ocean of superheated gas. We can't send a probe there, and we sure can't see inside it. So how on Earth, or I guess how on the sun, do scientists even begin to map something so mind-bogglingly vast and completely out of reach? Well, that's the challenge we're diving into today. To get a handle on the sun's weather, first you have to understand its storms. And deep inside the sun, there are two absolutely colossal flows of energy that basically run the whole show. And these aren't just gentle currents. We're talking about massive movements of plasma that define the star's entire personality. So let's break this down. First up, we've got something called differential rotation. All this means is that the sun's equator spins way faster, about 30% faster than its poles. It's a huge difference. Second, there's the meridional circulation. The best way to picture this is as a giant conveyor belt. It drags plasma from the equator up towards the poles on the surface, where it cools, sinks, and then flows back. Now, the key here is that both of these enormous flows are powered by convection, that constant, turbulent boiling of hot gas rising and cool gas sinking. This whole internal weather system is the engine that drives everything we see on the outside: sunspots, solar flares, you name it. So if you really want to understand these flows, you can't just look at them. You have to build them. Scientists create these incredible virtual suns inside supercomputers to try and mimic this behavior. But it turns out there are two totally different ways to do this, and each one comes with its own set of pros and cons. On one hand, you've got direct simulation. This approach is all about seeing the individual trees. It's like trying to track every single car in traffic, every little plume of hot gas as it rises and falls. It's unbelievably detailed, but so far, these models just haven't been able to reproduce what we actually observe on the real sun. Then, on the other hand, you have mean field theory, and this is what we're focusing on. This is about seeing the whole forest. Instead of tracking every car, it's like predicting a traffic jam by looking at the average speed of all the cars. You average out the chaos to find the big picture rules. It's a powerful shortcut, and it's the key to this groundbreaking new model. All right, so let's pop the hood on this new model. To get their virtual sun to act like the real thing, the scientists had to bake in some very specific, and frankly very clever, physics. The first key ingredient is something called the Coriolis number. Now, don't let the name scare you. In simple terms, this is basically one number that tells you how much the sun's spin is messing with its internal boiling. It's a measure of this constant tug of war between the star's rotation and its turbulence. Getting this number right is absolutely fundamental to making the whole thing work. Now, what's so cool is that the sun's rotation isn't just a simple spin. It actually creates this subtle but incredibly powerful force called the lambda effect. You can think of it as a hidden engine buried deep inside the sun. And this graph here shows how it works. It's actively grabbing momentum and pushing it around, forcing the gas at the equator to move faster than the gas at the poles. This is the hidden engine that creates that differential rotation we were just talking about. And here's the final crucial piece of the puzzle. This model accounts for the fact that rotation literally changes the way heat moves. Heat actually finds it easier to travel vertically, kind of along the axis of rotation, than it does to travel horizontally. This effect is called anisotropic heat flow. It might seem like a tiny detail, but it turns out this is one of the most critical factors in building a virtual sun that actually works. Okay, so the team built their model with all these key ingredients: the right balance of spin and turbulence, that hidden engine driving the flows, and this really clever way of handling heat. But now comes the moment of truth for any scientific model. Does it actually match reality? And you know, the ultimate test in solar physics is something called helioseismology. It's the science of sunquakes. By studying the sound waves that are constantly rippling through the sun, scientists can map its interior. It's just like how geologists use earthquakes to map the inside of our planet. This is the gold standard for checking your work. And the results, they were a massive success. Just take a look at this graph. The solid red line is the model's prediction for the sun's rotation speed. The dashed black line right behind it, that's the actual data from real observations. I mean, look how close they are. It's an unbelievably good match. The model absolutely nailed it. But it didn't just get the rotation right. No way. The model also successfully recreated that second great current, the meridional circulation, that giant conveyor belt. This diagram shows the model's prediction, one huge circulation cell flowing in each hemisphere. And guess what? That is exactly what helioseismology, the sunquakes, told us was happening. Getting both of these fundamental flows right, that's huge. It proves the model's core design is spot on. So with the basics locked down and confirmed, the scientists could really start to have some fun. They could push the model further and start using it to explore some of the sun's more subtle and weird behaviors, like its wobbles. Yeah, it turns out the sun isn't a perfectly symmetrical ball. It has these giant, slow-moving weather patterns called Rossby waves. Think of them like planetary scale vortices that just drift across the surface. This heat map here actually shows the model's simulation of these waves, with the red and blue areas showing the complex structure. It just proves the model is powerful enough to capture these much finer details too. So they ran another test. They took their stable model and basically gave it a virtual push to get these Rossby waves started. And what happened? Well, these graphs show the energy of those waves over time, and all you need to see is that all the lines are trending downwards. Just like we see in the real sun, the model predicted these waves are only temporary. They naturally just fade away over a few years. It was another impressive win for the model. But, and this is a big but, in science, success often uncovers even deeper questions. And this test, as successful as it was, pointed to a fundamental contradiction hidden deep inside the theory itself. Okay, let me translate that science speak for you. The entire point of the mean field theory was to average out all the small-scale, chaotic boiling of convection. But when the scientists ran this test, they found something kind of shocking. The model itself was unstable. It wanted to start generating its own convection, the very thing the theory was supposed to have already smoothed over and accounted for. It was an internal contradiction. Now, this might sound like a failure, but it's absolutely not. This is the scientific process in action. By building a model that was so good, so accurate at recreating the big picture, the scientists accidentally discovered a flaw in the underlying theory. This powerful new tool just revealed a deeper, more fundamental puzzle that needs to be solved. Which brings us to this fascinating two-sided story, which this table shows perfectly. On one hand, the model is a massive success. It perfectly simulates the two biggest flows inside the sun, and it even predicts the behavior of those complex Rossby waves. But on the other hand, its success revealed that the very theory it's built on has a problem. It doesn't fully account for convection, which means the scientists had to use a kind of artificial fix to keep it stable. So this model is both a huge leap forward and a giant signpost pointing to the next great mystery in solar physics. And it leaves us with this really cool final thought. This incredible model answered old questions about the sun's weather, but in doing so, it uncovered a brand new one about the very nature of turbulence itself. It really makes you wonder, what other puzzles does our star hold, just waiting for the next great model to come along and reveal them?